Welcome to the M-Cubed weekly seminar. And today we're very happy to have Kristen Rasmussen, whom a lot of you know from her days here at ASP. Kristen has a BS in meteorology and mathematics, and a BA in music from the University of Miami, and a PhD from the University in atmospheric science from the University of Washington. From 2015, 2016, Kristen was here as an ASP postdoc. In 2016, she joined the CSU faculty, where she is currently associate professor in the Department of Atmospheric Sciences. Kristen's research interests include investigating the global population of convective storms from the TRIM and GPM spaceborne precipitation radars, extreme deep convection in South America, flooding in Pakistan and India, cloud and mesoscale processes, high-impact weather, hydrometeorology. I think I'm naming just about everything in this field. Cloud-climate interactions, convection-permitting, and regional climate modeling. And today we're going to hear extreme weather in current and future climates, perspectives from convection-permitting regional climate and global climate models. Kristen, please take it away.
Thank you, Rich. I think I turned on this mic successfully. Well, it's wonderful to be back. The pandemic has put an interesting wall across the scientific community. I've just lived in Fort Collins, but I haven't been here for several years. It's great to see familiar faces, and it's really nice to be back here at the M-Cube seminar. So thank you for attending, and thanks for joining online. Okay, so today I'm giving a talk here on several different topics scattered across my research group at CSU. You can see a lot of co-authors here. My first PhD student, Erin Doherty, she's actually just started as a project scientist here at NCAR, so there's some nice connections there. I have a lot of postdocs, some students. Jim Hurl, Sue Van Heaver, and others have contributed to this discussion. Okay, well today we're going to talk about extreme weather in a current and future climate from several different tools. We're going to start and think about convection-permitting regional climate simulations, and then all the way out to global climate models. So for motivation, this is probably very familiar to many of you. Extreme weather has been increasing over the past 40 years. This is a figure here from NOAA showing the number of billion-dollar events in the United States from 1980 through 2021. And you can see that over time, across different types of events, these events are steadily increasing over time. In addition, in 2020, the World Economic Forum looked at globally the risks to global economies and actually highlighted, this is a call out here, of the highest likelihood and the highest impact types of events threatening global economies, and extreme weather and some other topics related to climate filter to the very highest likelihood and also the very highest impact. And so this is a really interesting and important topic to cover globally. Okay, so extreme weather. Where does extreme weather happen on our planet? We'll go back to this nice diagram looking at lightning flash rate from Ed Zitzer's paper from 2006, looking at where the most extreme deep convective storms happen on our planet. And it actually turns out that these hotspots are actually co-located with some of the largest mountain ranges we have on our planet, the Andes, the Rockies, and the Himalayas. The reason that we see these deep convective hotspots is these places all have a combination of low-level moisture advection. We're bringing in low-level moisture from somewhere, and we have some sort of dry air or upper-level capping inversion that's basically allowing for that instability to grow. These environments require both convective instability and inhibition across this global spectrum. And this allows, again, for that buildup of convective energy that is critical for generating the deepest storms that we see on Earth. Okay, but I'd like to suggest that if we think about research at the intersection of weather and climate, this is a really interesting intersection. This is how I'm centering my research group, actually, is to be right at the intersection of these two fields. To do this research, we really need improved understanding and model representation of clouds and their environments across scales. Here's a nice example from Chu et al. 2022, showing you take some kind of emissions scenario, you look at how changes in global circulation and climate look on global scales, you then can downscale that to look at more specific high-resolution perspectives like rainfall, and then in this example, they go all the way down through hydrologic modeling. All right, so the framework we're going to use today, I have an umbrella. We're starting thinking about extreme weather in a current and future climate. I'm going to step through some of the different questions that we'll answer and talk through today. The first question is, how do three-dimensional extreme storm structures change in a warming climate? To do this, I'm going to use convection-permitting regional climate simulations, actually led by teams here at NCAR. I will then look at how do the environments supporting extreme weather change in a warming climate, particularly thermodynamic environments. And we're actually going to look at these in both convection-permitting and global climate models to see both how they compare and what we can learn that's different from those two frameworks. The third question is, what is the uncertainty in estimates of these environments supporting extreme weather in a warming climate? We're going to use the CESM large ensemble to do this. So we'll basically be looking at these global climate models to see what's the uncertainty of these convective environments from these larger scale models. And then finally, would estimates of global convective mass flux help constrain problems we have in models across scales? And so we're going to look at both of these scales to understand how this might be important. Okay. So let's get started. The first part here, we're thinking about an investigation here of extreme weather events in convection-permitting regional climate models. Probably many of you have seen these simulations. These are the CONUS-1 simulations run by a large team here at RAL and M3. These are 4-kilometer convection-permitting regional climate simulations over this entire domain here, seen on the right-hand side over the United States. These are run for 13 years in the current climate for forced with era interim reanalysis. And then there's a second experiment using a pseudo-global warming approach. Basically, you take that same 13-year period forced by the era interim reanalysis, you apply a climate delta signal. This is how this is calculated. It's a 19 CMIP5 model ensemble monthly mean condition that's taken from a 30-year period in the future climate, subtracted with a 30-year period in the current climate to basically get how these environments may change in the future. Temperature, moisture, what are we doing in 100 years and how does this change? We're adding that to the forcing and then we drive that model again for 13 years. Interestingly, a really interesting study by Beck et al., 2019, showed that this exact WRF-CONUS simulation here in the middle line is the variability ratio, so you want to be at 1 to have the lowest bias. And actually, this WRF model actually had the third best variability across a lot of these different models. You can see Persian, you can see CHIRPS, ERA 5, some different parameters here. And it also had the lowest bias in precipitation over the Intermountain West. So it does a really good job of reproducing the precipitation climatology. Why does it do this? First of all, at 4-kilometer resolution, it's resolving those topographic features. As we live here in Colorado, well, I live here, many of you do too. The mountains play a really big role in the convective population, the life cycle, the initiation, and we're starting to resolve some of these features, showing we have a peak diurnal cycle in the nocturnal hours, which we do expect and we see in observations. We also reasonably reproduce the diurnal and seasonal cycles of organized precipitation, propagating organized MCSs and such. And this also allows for convection to allow naturally in its environment. We do not use a convective parameterization, and so these storms are responding to these changes in the environment in a natural framework. So this is actually work I started as a postdoc here. Basically, what I want to do is look at this hourly output for 13 years, and I want to calculate the frequency of occurrence within 6 reflectivity ranges. Radar reflectivity is a measurement of the size and the density and the concentration of these particles within the storms, and I wanted to look at how this changed in a future climate. So to start here, this is 0 to 10 dBz, 10 to 20, 20 to 30. These are weak to moderate types of ranges, and we're seeing that these ranges over a lot of the eastern United States actually decrease in frequency in the future climate. This is the future minus the control. As we get to stronger and higher reflectivities, representing more extreme storms, we actually see more reds in this pattern. And I've summarized this here in May and June on the top, July and August on the bottom, and I use a Great Plains averaging region and then the full CONUS. What we're seeing is that at these low to moderate reflectivity thresholds, we're actually seeing broad decreases in the number of these events in a future climate. But as we tip more into these extreme higher reflectivity values, we actually see extreme increased frequency of strong storms in this framework. This is actually indicating a shift in the convective population. Everything doesn't just get more frequent. We're actually seeing a change in the convective population in a future climate. And I'll come back to this when we talk about the thermodynamic implications of what this looks like. Okay, so I'm going back to this statement. Research at the intersection of weather and climate really requires this improved understanding of clouds and their environments across scales. This is basically for the M3 seminar. thinking about how we can do this, these models sit right at the middle. But one of the really critical things that I was asked actually when I first published this paper after being a postdoc here is how well do convection-permitting regional climate models represent precipitating systems in a current climate? We need to know that these models are doing a good job of representing the current mode of convection that we see in our current climate. So I went back to my experience with the TRMM and GPM satellites. We're using these heritage modes. Basically, we're identifying very specific three-dimensional structures in both horizontal and vertical space. The first one I identify is a deep convective core. This is a contiguous 40 dBz echo extending above 10 kilometers. This is the metric that was used to identify the most intense deep convection globally. I also look for really wide connected systems. This is 40 dBz echoes over 1,000 kilometers squared in the horizontal. I call these wide convective cores. And then I have an overlap category if they meet both thresholds. They're called deep and wide categories. We've used this successfully globally. This is an example from TRMM, where we look at the deepest storms on Earth. We see they primarily are continental. If you look at shallow isolated that are less than 5 kilometers, predominantly over oceans, and organized convection happens across, you see some ITCZ behavior, and some more of the continents are filling in. So we've used this from a global perspective to understand what the population of storms look like in general. So we now take this same framework, and we're applying it to that same CONUS data set. So we've now said, okay, here's the tornado super outbreak from 2011. Let's apply a convective stratiform mask, as you can see on the top right here. And now we're identifying storm modes of these same TRMM heritage types in the model simulations. We do this for all 13 years in the current and the future climate, and these are the results. I also have GPM observations on the top because GPM is extended to 65 degrees north, and so we now have a much greater sample. And what you see, if we look at deep convective events, this is the CONUS control simulation. We see a hotspot here. There's an interesting hotspot right here, actually, along the Sierra Madre in Mexico. We actually see that hotspot in the TRMM data. We don't have as many years of GPM data, so the points are not as frequent as we would like. We do see, though, that qualitatively, the locations where we see these storm modes across the GPM and the CONUS data sets look quite good. So we're getting the right storm modes in the right places. We're also getting the right storm modes at the right time of the year. So here's GPM observations on the bottom, January through December, the same plot on the top with the same colors for the same storm modes for the CONUS simulations for the same time period. And so we're seeing similar cycles during the year. We're seeing similar locations. So this seems to indicate that the fidelity of these CONUS simulations are doing a really good job in representing and reproducing the existing climatology of storms that we see in the current climate. Okay. Now, you may be wondering what happens in the future climate. We also did that same calculation. So the same data is here on the left-hand side. This is the future climate frequency distribution, and this is the difference, okay? So here's the 3 convective categories on the top. They're pretty small figures, but you probably just see red. They're basically all red. We're seeing basically very strong increases in the number of extreme convective storm modes in the future climate, just like we saw with the previous reflectivity analysis. When we look at these specific storm modes, though, here are the percentage differences. We're seeing about 180% increase in the deep convective core structures. We're seeing 43% or 44% increase in wide convective cores, and we see almost 250% in those deep and wide systems. Those are, yeah.
Could you go back one
Yeah.
slide? What's interesting is there's a lot of area where there isn't much change. Right?
Yes. Mm-hmm.
So it's not everywhere.
It's true, yes. Yeah, there are some places, for example, where you see maybe some up here. Yeah. Oh, sorry. Yeah, Morris was saying that it's interesting to see that there are actually quite a few places where you don't see much of a change. We do, for example, see a lot of changes over, east of the Rockies in the Great Plains, southeast region of the U.S. Not as much along the west coast. There are some interesting increases along the Pacific Northwest for a particular storm mode, but we're digging into those details seasonally as well. Yeah, great comment, thank you. Okay, so we are seeing really big increases in the convective modes, and the stratiform precipitation, we're actually seeing it stays relatively similar. So that's an interesting comment there. And if we look at this, the monthly changes by storm mode here, we're seeing that these increases are primarily happening in the saddle seasons. So in the fall and the spring, this is when these convective modes are really ramping up relative to the warm season. All right, so let's go back. Let's think about this as a conceptual framework from that original figure I showed you from my old paper, looking at moderate to weak systems decreasing, extremes increasing. I'm interested in studying the environments that support these extreme events in a future climate. What is the reason for this shift? Why are these storms shifting in this particular way? To do this, we're going to look at thermodynamic environments, both in the convection-permitting models and also in climate models. All right, so we go back to this. Again, we need both of these two pieces, instability and inhibition. So we're going to look at this in both of these models. I just said that. I went ahead of myself. All right, so this is from the CONUS runs. I have convective available potential energy. This is the amount of potential energy available for convection if it can tap into it. Control on the top, PGW in the middle, the difference on the bottom. Again, similar to what we saw before, east of the Rockies in this kind of Great Plains into the southeast US, we see basically just increases in CAPE. It's a warmer, moister climate. This is an expected result that we've seen from many studies in the past as well. Let's look at convective inhibition. This is the energy that is basically suppressing convection. You have to break through or overcome convective inhibition in order to realize your CAPE. So here's again control, PGW, and the difference. What we see here is that we actually have an increase in the magnitude of SIN. There is more energy in the future climate inhibiting that convection from forming. And so we think that this is the reason that we're actually getting fewer weak to moderate systems, right? They're preferentially suppressed. They're not able to break through this stronger cap. But if you can break through that stronger cap, you can tap into much more CAPE and become more severe in nature. We looked at the phase space. This is control, SIN on the top, control on the top, PGW on the bottom, and SIN on the y-axis, CAPE on the x-axis, and these are 2D histograms, showing that in the current climate, we have this distribution for all of these points for 13 years. In the future climate, we are actually extending to a much different phase space. We're at higher CAPE, and higher average SIN. So these environments are not realized in the current climate in an average sense, but we are seeing them in the future climate. And so we're understanding this shift in the population in this way. As a result of this work and some collaborations with Igo Dai and his group, we looked at this in error interim reanalysis across the entire globe on the top. We also looked at this in 6-hourly data from CCSM4. This is GCM data sets, okay? So if you look at the US, right, think about those same patterns I just showed you. The agreement is actually quite nice. We see similar things where broad increases in CAPE, broad increases in the magnitude of SIN. If we look at this in this type of phase space, here's the 1980 to 1999 mean, showing basically this same kind of 2D histogram like I showed before from the climate model. And then on the right-hand side, this is 2080 to 99 minus 1980 to 99. So you're seeing, again, that same shifting down to higher CAPE values and higher magnitudes of SIN. This is now a direct comparison of the WRF-CONUS runs, those differences that you saw before, relative to that 6-hourly GCM data on the bottom. You see some nice comparisons. So the take home here is that these changes in the thermodynamic environments that support the deepest convective storm modes on Earth are actually really well represented in GCMs. They do a really good job of getting those environments. But we wanted to take this a step further. And one of my students, co-advised by Jim Hurl, Megan Franke, wanted to take a look at this in the large ensemble. So we're now interested in what is the uncertainty across these environments if we look at a 50-member ensemble from a climate model, okay? So this is the CSM2 lens ensemble. We're using the SSP3 7.0 emissions scenario. You can see it here in this red line. So it's not the worst, but it's not the best. It's kind of in the middle of the road. And she's looking at daily data for these parameters to calculate these same parameters that we just talked about. How well does the lens ensemble do with looking at CAPE SO6? This is a product of CAPE and shear between 0 and 6 kilometers. Here's AR5 on the left. Here's the 50-member ensemble mean on the right-hand side. And you see it actually does a relatively reasonable job of capturing this climatology. Megan also did a linear regression of CAPE SO6 onto the ENSO index to see what about the variability? How well does it do spanning that variability? And you can see actually between AR5, this is a single 40-year record. This is on the right-hand side, 50 members for a 150-year-long record. And actually these patterns, there are some differences, but they qualitatively look actually quite similar, which is very encouraging. We also looked at this over a really long time scale. The large ensemble provides a really excellent range back all the way to basically 1880 all the way to 2100. This is one of the exciting parts. On the right-hand side, these are boreal spring anomalies of these different parameters, CAPE as shear from the 0 to 6 kilometer level, product of CAPE SO6, and convective inhibition. The black line is the ensemble mean across that 50-member ensemble, and the gray lines are the spread, the uncertainty in those environments in these runs. What you can see, actually, really interestingly, is that the CAPE, let's focus on CAPE first, it's pretty flat, actually, for a very, very long time across this range. Just before 2000, it starts to tip up, and you can see that by the end of the century, almost all of those ensemble members are positive. They're all in agreement that CAPE is going to increase. It's just when it actually reaches there, depending on the internal climate variability of the individual ensemble member. We also see CAPE SO6 going up. We see, actually, interestingly, over the United States, the 0 to 6 kilometer shear is looking like it actually might decrease. A lot of the ensemble members show a decrease, but you can still see, even by the end of the century, there are still some ensemble members that are positive. So it's not, a given that this is happening, but this is what's happening in this model. And we do see SIN, convective inhibition, is increasing in magnitude. Starts off about the same time, just around 2000, starts to decrease. So decrease or increase in magnitude, SIN is a negative quantity. So we're seeing some really similar aspects in the longer term record. What about, oh yeah, sorry.
Real quick question. What's the region of this analysis? Is this the whole Earth, or is this?
This is the eastern US. So it's basically kind of like Great Plains. Yeah, sorry, I forgot to show the box. Yeah. So this is focused in on that eastern part of the United States. Sorry for missing that detail there. You can kind of see some of this. It's basically a box centered over the eastern part of the US. Let's look at this with epoch. This is really exciting. For the large ensemble, we can actually look at different time slices. With the convection-permitting run, we have a single view in the future. Now we have different epochs. And you can see, let's step through CAPE. This is 2021 to 2050, 2041 to 2070, 2071 to 2100. You see that these changes are accelerating as we go toward the end of the century in the spatial view as well. Okay, Megan made this really nice figure, kind of inspired by my figure from the convection-permitting runs. But we now have this by epoch. So the blue distribution is the current. The orange distribution here is from 2021 to 2050, so an earlier time period. And then the green is 2071 to 2100. And we see this similar shift down to the right, higher CAPE and higher magnitudes of SIN, just like we saw from the regional climate model as well. This kind of looks somewhat similar to what I previously showed from the high resolution model. She also looked at these distributions for SO6, so the shear from 0 to 6 kilometers, and CAPE, and we see a similar tip down. Although lower shear is actually not good for the generation of severe weather, as this nice figure from Brooks et al. Shows. Here's the distribution for CAPE and shear from 0 to 6 kilometers, and the farther to the top right of the diagram you are, the more likely you are to have a significant tornado or very severe weather. So this is an interesting thing to consider and how it may affect the population here in the United States. Okay, we also looked at this in South America. I just want to show this really quickly. We did the same thing. This is ERA 5 CAPE, CSM large ensemble on the left, ERA 5 on the right. It looks quite good over South America as well. And if we do this linear regression of CAPE SO6 onto the ENSO index, we get some really interesting, fairly consistent patterns, just like we saw for the US. We do see similar types of distributions for these different parameters, although one thing I will mention, this is a trace here for the entire continent, but when we look at just the subtropics, the SO6 actually goes up. So it's a very interesting difference that we're seeing in the large ensemble in subtropical South America relative to the US. Okay, we're going back to this conceptual framework. I'm also really interested in studying extreme events in a future climate. So thinking about what do extreme events look like and how can we characterize what how they look and how they may change in a future climate. So to do this, I'm going to feature some of the work from my previous PhD student, Aaron Doherty, who's now here in the NCAR team. We're looking at floods. So floods are extremely impactful. They're one subset of extreme events that are extremely important to look at. Here's an example from Hurricane Harvey. Here's the highway before. Here's the highway after. This was an incredible amount of rain. We've broken a lot of state records recently. We continue to do this globally as well. Here's an example from Typhoon Morakot in 2009, showing extremely challenging situations with heavy rainfall. We expect that future floods will cause more damage. So this is an estimate here, a present-day value of assets in floodplains. And this is showing the percent increases in the future climate just to assets exposed to floods. Not necessarily the increase in the floods themselves, but just we're going to have more population and assets in these floodplains in the future. We also expect that global flood risk is projected to increase. Here's an example here from Hirabayashi et al. In 2013. Some great work from the team here at NCAR showing that these convection-permitting models show that future hourly precipitation extremes are going to increase over much of CONUS. Our work, though, we're centered really carefully around the specific flood-producing storms. So flash flood-producing storms, we want to look at this very carefully. So Erin did some great work. This is how she did it. She took a flood centroid from the NCEI storm events database, shown in the star here. She then connected this in a hydrometeorological sense to stream flow indicated floods from the Shen et al. Database. This was one of the first times we were actually able to really carefully connect atmospheric rainfall to the occurrence of floods on the land surface. And she omitted floods that were greater than 3 days and 200 kilometers from those stream gauge floods. She then looked 5 degrees in each direction and took the 75th percentile of accumulated rainfall from the 4 kilometer stage 4 data set. She also developed this really exciting new, she applied this new tool from the image processing industry, actually, that looks at the structural similarity between basically 2 images. So if you have 2 images and you're in the image processing industry, you want to know, is it a cat in this one and a cat in this one? You can apply this index. Basically what this is some samples. You have a mean pixel intensity and the variance, and you're looking for a range between -1 and 1. The closer to 1 you are, the more similar those are in both structure and intensity. She looked at this across all of the floods that she pulled from this data set in the CONUS simulations and found we had really high similarity in the structures. And this is the control and then the PGW showing those differences. So these floods were being structurally well represented in this situation. She recovered 584 cases from these model sets, and that's what she'll be looking at in this work here. All right, so one really interesting aspect of the CONUS run is that because it's a pseudo-global warming technique where you're taking basically a perturbation, you're adding it to the reanalysis signal, we actually preserve synoptic flow features in these runs. We can look at a flood in the current climate, and we're just adding temperature and moisture and other perturbations here, but we still have that trough. So this is the flood we're looking at. This is an example of 500 millibar heights in the control on the left, PGW on the right. Here's mean sea low pressure, precipitable water, and winds. You see we still have this kind of feature of precipitable water coming up. We have a low-level jet bringing that in. It's just a little moister, but these same features are in the pattern. These are the 2 floods. This is the control flood. This is the PGW flood, and we're going to compare the characteristics of these floods in this analysis. What she found is that flash floods become more intense in the future climate. This is an estimate here of the maximum rain rates within these systems. Control distribution is in blue. The future climate, PGW, is in red. We're seeing a shifting to the right of the maximum rain rates within these systems. We also see that the percent change per Kelvin is shifting to the right. The mean change that we're seeing within these systems is about 15.7%. The median is closer to 7.5, which is much closer to the Clausius-Clapeyron theoretical rate. If we look at composite area rainfall, we see much increased area average rainfall in the future climate associated with these convective systems. If we focus on the Mississippi River, we see much higher values of total rainfall per storm. This is per storm. The difference is on the right-hand side. We see increased runoff per storm here, shown in the difference. The difference is the blue colors mean there's more runoff or rain in the future. She then also divided this by vertical velocity. So we wanted to look at the intensities, some of the dynamical pieces. So we basically divided this into weak, moderate, and strong distributions here. And what we show here is that basically the maximum updrafts are stronger in a future climate. We're seeing increases in the maximum updrafts at all of these categories in a future climate. We also see that the volumetric rainfall from the control to the PGW through the stronger storms, we're seeing the most increase in volumetric rain when these storms are stronger and more intense. We also looked at vertical profiles of moisture and vertical velocity. So this is basically vertical velocity here. The red colors are the future climate, the blue colors are the control, and then the different line types are weak, moderate, and strong. So you see that the future climate, we're seeing actually really big increases in vertical velocity higher up in the storm. We're seeing, if you look at mixing ratio changes, we do see some moderate changes. We have moisture conditions, but if we want to look at a vertical moisture flux, which is a really important aspect in thinking about the conversion into rainfall, we see that the largest contribution is, in fact, from the vertical motion aspect. Okay. So I'm going to bring this back. We're going to talk now a little bit about what does this mean. Vertical velocity, we saw that it's really important in understanding the future dynamics of the systems and the storms that we see. But vertical velocity is extremely challenging to measure in the current climate, and it's very challenging to model, both convection-permitting scales. I just had a discussion with Andreas Prine yesterday. Even if you go to 250-meter resolution, you still have a lot of challenges in the intensity of the systems being overestimated. We actually have no, despite all the advances we've made from spaceborne radars, we currently have no platforms that measure vertical velocity from space or some of the dynamics of these systems. We do not have those measurements. In addition, our highest fidelity models at very high resolution overestimate vertical velocity by a lot, sometimes on the order of 200%. Like I said, I just had a discussion with Andreas yesterday about this is happening in 250-meter resolution as well. At the same time, GCMs, they parameterize convective mass flux, or basically the movement of the mass of air and water in the atmosphere. These parameterizations are built a lot of times on these outputs from these numerical weather prediction models at finer scale resolutions. So these are errors that are basically around that we have no observations globally to constrain. So we, and led by Sue Vandenhever, are now working toward a new satellite mission called Incus. Incus is Latin for anvil, so you can think it's a very storm-focused type of mission. It's the new Earth Venture 3 mission. The goal of Incus is to understand why, when, and where tropical convective storms form and why only some storms produce extreme weather. Let's take a cross-section here from A to B. Here's a cross-section. So if we're thinking about in this storm, how much of the air and the water in that mass is moving up in the atmosphere, that's basically our convective mass flux. Incus is trying to measure this, and this mission will be the first systematic measurement of convective mass flux from space. These are critical observations that we really need in general. What does it look like? I'm learning a lot about small sats and engineering of small sats. This is a new thing for me. But basically what this is we are flying 3 small sats. There was a mission, a NASA tech demo called RainCube that flew a microwave-sized Ka-band radar successfully in space. It was really exciting. We're putting 3 of those. We have 1 on each of these platforms. We have a microwave radiometer that is a Tempest D heritage, another NASA tech demo, led by Steve Rising from CSU. And we're putting basically all of these in tandem, and we're separating by 30 and then 90 seconds, and then 120 seconds between the first and the last satellite. The idea is in the flight direction, we're hoping to resample the same systems. We have a very strict overlap criteria, where we have 7 beams of the radar, and we are ensuring that we have at least 80% overlap so that we do in fact see the same systems over these very short timescales. Okay? All right, convection evolves rapidly. These are some classic images from Ted Fujita. This is just a 20-minute time scale. Here's a nice movie. This is a 30-minute period from the beginning to the end of this movie. Convection evolves very, very quickly on very, very short time scales. So how is Incus going to measure convective mass flux? It's not a Doppler system. We are just sampling rapidly in time. We have a delta T approach. This is basically an idea where we have basically rapid movements of air and water. We can see changes in the volume of the system. We're going to be tracking those changes in the volume in time. So this is essentially, you've probably seen this, you've probably drawn this with your kids or grandkids, that you can make a crude cartoon, right, by simply taking the difference of 2 images. This is the concept of our approach, where we're sampling it at 3 different time intervals. The short time interval, we'll see the really deep, very vigorous types of convection. The longer intervals are going to see more of the moderate and the weaker systems. So I would like to suggest that there are really exciting future opportunities across this landscape to better constrain convective mass flux and convection-permitting through global models. And we can kind of have a space and a discussion across these different frameworks that are currently really challenged without having those observations to connect in time and space. Okay, so back to the conclusions here. So we saw changes in the convective population. We saw that there were fewer weak to moderate storms, more extreme storms in the future climate. There's a shift in this convective population. It's not just everything becoming more frequent. There's actually a change in the partitioning. We had significant increases in intense convective storm modes seen from the three-dimensional storm analyses as well. We then wanted to say why. Why is this the case? So we looked at thermodynamics. CAPE is increasing everywhere. There's more energy available for convection to form. It's a warmer and moister climate in the future. Convective inhibition also increases, and a lot of our models are showing that it's increasing almost everywhere, particularly over land. There's more energy inhibiting this convection, stronger capping inversion to break through, so it's actually preferentially suppressing the weaker systems. So those weaker systems are likely not forming because they can't break through this cap. If you can break through this cap, you can tap into much higher CAPE, and you might be able to be a little bit more intense in terms of your vertical dimensions. We saw consistent results in models across scales. We looked at convection-permitting regional climate simulations, GCMs, and we looked at uncertainty across the 50-member lens ensemble, telling us which of these environments we're actually pretty confident about, which is a new dimension to this research. And I said this before, but we think that this may explain, these thermodynamic environments may explain why we see these fewer weak and more extreme systems. Second part, we looked at flash flood producing storm rainfall and runoff. These increase over most of the CONUS in a future climate. We have more intense vertical forcing in these strongest storms. This leads to enhanced rainfall in the future associated with flash flood systems. It indicates the importance of both dynamics and thermodynamics in understanding future storm populations. And so this is something I'm continuing to think about as we move forward. The vertical moisture flux is a really key ingredient for precipitation. Increases primarily due to the vertical velocity in the future climate. We talked about how this vertical velocity is very, very hard to measure. We have very few measurements of it, even on the surface. Dual Doppler, wind profiler types of efforts still have a lot of uncertainties embedded in them. This new Incus satellite will then provide the first global estimates of convective mass flux. If you're wondering, we're launching in 2026. We'd love to have a lot of collaborators and people looking at the data. Implications for improving models across scales, which I think is very exciting. So with that, I'm going to leave you with my question slide. I have a movie here created by a JPL graphics design artist showing some really interesting eye candy of what Incus will do in the future. So thank you for your attention. Thank you again for the invitation, Rich, and I'll take any questions.
Okay, we have a number of questions. Let's see. I have to do this systematically. Start here, and we'll work our way back.
So, Kristen, great talk. I've got a quick question for this pseudo-global warming approach. This is very nice approach, and I know quite a bit about it. But to me, one of the key questions is that basically the assumption is that the weather pattern doesn't change. So let's say storm tracks stay in the same place. You just have more water vapor to work with, if you like, and it's warming, so it's warmer. But of course, part of the climate change is shifts of storm tracks. So
yes.
To what extent are you comfortable, and can you extend it to, for example, move, let's say, weather north or south, depending which hemisphere you are, to kind of account for that, according to what climate models are doing, because they presumably do quite well on storm tracks, for example.
Yeah, that's a great question. That's one of the reasons we decided to use some different approaches, actually. So the climate models and the CSN large ensemble in particular, that ensemble is representing changes in storm tracks and things like that. So we were wanting to look at those environments in that context to understand how these environments may be shifting relative to what we see in the convection-permitting runs. The pseudo-global warming approach does a great job at the thermodynamic aspects of climate change. It doesn't represent as many of the dynamics. That's why I was focusing on the shear with the lens simulations, right? Because we are seeing storm track changes and maybe some important changes in the shear. We can't really look at shear in the PGW runs. So I think a varied approach is what we're taking. There are current efforts, for example, to directly downscale from a climate model down into a high-resolution regional climate model. So you actually would then represent those changes in the storm tracks. Those efforts are ongoing. IGODI is leading one of those simulation sets. So I think there's a lot of thinking on that. But yeah, that's one of the reasons that I like to use multiple approaches to address the same question. Thank you. Yeah.
Yeah, basically just repeating his question,
Yeah.
maybe a little more specifically to the flash flooding situation where it's not just thermodynamics, but there's mesoscale, synoptic scale forcing.
Yes.
And you're not really
Yes.
predicting any changes in the forcing elements.
Yes.
So that, similarly is perhaps a limitation in the conclusions, right?
Yes, I mean, we are limited to the PGW framework where we're not representing those larger scale, larger than monthly types of variability. But what we are seeing changes in the storm dynamics. So the thermodynamic changes are actually changing the local storm scale dynamics within the storms, even within the same synoptic scale forcing. But yes, you're right, in order to look at this, maybe looking at those downscaled runs, for example, with similar types of systems would give us a different answer, taking that aspect into account. Yeah, thank you.
Hi, Kristen.
Hi, Chris.
My question is about the CAPE and SYN relationship. I think you
Yes.
were implying that the CAPE was increasing more or less because there was more inhibition. I don't know if that's what you were saying.
No,
They're just
yeah.
they're correlated. I guess I'm trying to figure out what the driver is in this correlation and why inhibition would be increasing in the future scenario.
Yeah, it's a good question. I was not implying that they are directly connected. They are related. But the increases in CAPE, we see this in RCE simulations, for example. David Romps has done some nice work showing that basically with warmer SSTs or warmer temperatures, the CAPE equation is essentially just temperature and moisture. So that's really the main reason is those changes in the system. For SYN, we actually looked at this a little bit with the paper with Igo Dai, where we actually saw really significant changes in low-level relative humidity, actually, over the continental U.S. That was actually one of the main drivers that we think was affecting the changes in SYN. We're still looking into some of those details, but that was our first view from that work. I don't know if that answered your question, but yeah.
Okay, my turn. So I'm curious if you were able to look at whether the duration of the convection changed. So
Yes.
longer time periods, shorter time periods.
Yes, that's a great question. Andreas Pine has done a lot of great work kind of tracking MCSs and looking at these types of things. There are some changes in duration. There was a nice paper also from Ethan Gutman looking at differences in tropical cyclones, for example, with the pseudo-global warming approach. I would like to actually run a storm tracking connected to the storm mode perspective for some of our runs, but I haven't looked specifically at duration, but that's something I'd like to work with Andreas and others on. So, yeah, good question.
So my question is, you showed that, especially in the eastern U.S. and South America, that CAPE really started increasing and the magnitude of SYN also started increasing a little before 2000, and it's basically a linear trend in both regions. I'm wondering, have you looked at all at observations, say from soundings? I agree it's far fewer data points, far smaller sample size, but have we been able to observe those changes that the lens model predicted in these large-scale changes in CAPE and SYN, say from 25 years leading up to 2000 and the last 20 years leading up to now?
Yeah, that's a really good question. I know there's some efforts to compare what thermodynamic parameters look like in reanalysis data products. And I think I have to go back and look. I haven't read those papers recently, but yeah, that's a really good question. Yeah, especially because it is showing that tip up around the 2000 timeframe. I haven't looked at that, but that's a good question.
So we're going to take a question from Slido.
Oh, yeah.
What is the ideal latitude range that Incus can operate, having estimates of vertical motion in mid-latitudes where we have substantial UTLS convective mass transport would be great?
Yes, thank you for the question. Our ideal inclination is about 39 degrees. We've done a lot of calculations. In fact, going back to some really classic work of how many thunderstorms are around the planet at any given time, we've done a lot of theoretical calculations on that. Our ideal latitude is inclination is 39 degrees, but we have actually been considering some launch options going all the way up to 66 degrees. So anywhere in that, we're a smaller mission, so we need to either do a ride share or a smaller dedicated launch. That will be decided by NASA in the next year or so. So we're being flexible, but our ideal inclination is about 39 degrees. But we might get up to mid-latitude frameworks if we have a higher inclination.
Thank you, Rich. Thank you so much for such an inspiring seminar. To be honest, I don't really have a background in convection, but I got very curious on a couple of aspects. The first is when you simulate the MCS, what do you think, how do you feel about the wind speed at the surface? Because, for example, even at 25 kilometer, it can be quite tricky to resolve the peak intensity of MCS. And this, of course, is a bit of a problem if you look at extremes over 70 years, because you just lose them compared to cyclones or tropical cyclones.
Sure. Yeah, it's a great question. I mean, at 4 kilometers, it's kind of a sweet spot that we are able to do long enough simulations that we get enough statistics that we can make really meaningful comparisons. We're not resolving convective updrafts, right? We're resolving more mesoscale features, so there are some caveats there. But we found that it actually does a reasonable job. Even if you go down, Andreas has done some nice work going down to 1 kilometers, down to 250 meters, 100 meters. You're getting the right general shape and a lot of the right structures, but you're missing a lot of the detailed, entrainment and all of those detailed that you get when you get to really high resolution. So there are a lot of caveats there, but the other thing is, if we went to 1 kilometer or 250 meters, we wouldn't be able to afford the long enough climate simulations to make those statistics viable. So it's kind of a sweet spot, right, where we're resolving topography, we get organized systems, we can turn off the convective parameterization, we're generally representing those structures in a reasonable way, and it enables us to run really long simulations with available computing time. If we had more computing time, sure, we could maybe run higher resolution, which would be ideal. There's actually really exciting digital twin types of efforts, right? ECMWF is running 1 kilometer models globally compared to satellite observations, and it looks quite good. It looks really exciting. We can't quite run those on long timescales yet, but we're getting there, right? It's exciting to see what will come in the next 5 to 10 years. I don't know if that answered your question, but yeah.
Yeah, I was also curious to know, how do you feel about the wind speed at the field?
The wind speed, yeah. Oh, yes. Okay, he's asking about how do I feel about the wind speed, the local wind speed, like near the surface?
Yeah, exactly.
Yeah, I haven't looked specifically at the surface wind speeds. We've looked at some things like cold pools and other types of, flow features within the mesoscale systems, but I haven't compared, for example, observations to some of these case studies. That's a good idea. Yeah, thank you.
Hi, Kristen.
Yeah, hi.
You briefly mentioned that some people are already starting to do like downscaling simulations from GCM runs in like 100 years from now.
Yes.
What's the holdup to making that happen? It seems like the cost is about the same as pseudo-global warming runs, right? So it's,
Yep. Mm-hmm.
Why isn't it, it would kind of alleviate a lot of the concerns people have.
Sure, yeah.
about
So
pseudo-global warming type
the
setup.
control run is already finished. I see Tim in the audience. I think there have been a lot of priorities. Well, this type of effort has become really popular, and I think there maybe just aren't enough people to kind of complete all these runs. The control run is actually available. So the control climate that's downscaled from the climate model is available actually on the NCAR RDA. I believe that the plan is to actually try to finish the future climate run before Cheyenne is decommissioned. I don't know, Tim, if you have any updates, but
I don't know if I need a mic.
You do.
yeah.
We're doing it on the USGS supercomputer, and it
Yeah.
should start.
You could.
We're about ready to. Right. Yeah. So the question about the CONUS, the new CONUS 404 runs for 40 years at 40 kilometers. We've actually got 43, I think, in the retro. So the retro's done. We're moving it to the RDA. Sizzle told me it's going to take 2 or 3 months, which a little frustrating, but I understand.
Yeah.
The data are on our system, but we're doing these runs on the USGS supercomputers. The PGW future run, which will start in water year 22, is ready to go. We're migrating the data over there probably this week, so it should start in the next week or so. It takes 11 months. We're using a quarter of their system.
Yeah. So these are 40-year runs, but this is the PGW. But we're still working on this direct climate downscaled simulation that IGO-DI is leading. So, yes.
Okay.
So hopefully they'll be available soon. I can't wait to get my hands on that data when it's available. So.
That's nice to know, but I still don't understand doesn't really address my core question, which is why people why do I see more pseudo-global warming runs than actual global warming runs? Like, what's the technical challenges, or why is it harder, apparently, to do one run over the other? Let's do actual global warming rather than pseudo-global warming, I guess.
I don't actually think there are that many technical challenges. Like I said, the control run is already ready to go. The benefit with the PGW is that, like, if you're working with a group like the USGS that wants to look at dry years and wet years, right? They want to look at specific things that they've observed with their data records. The pseudo-global warming record, because it actually uses the reanalysis, more closely tracks basically what happened with the additional thermodynamic forcing. With the climate runs, you have to look at statistics over long periods of time. You can't look at droughts versus, you have to look at those as their own independent data sets. Whereas with the pseudo-global warming, you can actually say, okay, 2000, this particular year was a drought. Let's look at what happened when we had a little bit warmer and moister conditions. And so those types of runs have been more popular. I think because the stakeholders and the applications of those downscaled runs are a little bit more tangible for applications. But I agree that the downscaled climate model run, I can't wait to see it because I'd like to run the same statistics and see how they're different, right? It's a really important comparison that needs to be made.
I think a clarification, PGW, you basically take reanalysis data and shift, the whatever temperature and moisture. So with a climate model, you don't have that kind of data in 2100 because the resolution of reanalysis is higher than.
You have GCM forecasts, so why don't you just replace reanalysis with GCM?
But the analysis has a better resolution. I think you have weather basically, and you have it already on every hour or whatever you're using. So I think that's the main reason. But in principle, you are right.
I would also argue that we probably would need a longer run, actually. I don't think 13 years would be long enough. You probably need something more like 20 to 40 years because you have to then average over long periods of time. With TRIM and GPM, with 16 years, we got really great statistics. But shorter than that, you see a lot of speckles. You saw the GPM figures here. So we might need longer runs in that framework as well to robustly compare those statistical systems.
So I don't think the crowd is quite exhausted yet. So we have
Yeah.
we have another half hour to meet and greet out here. And but thanks again for the formal presentation.
Thanks, everyone. Thank you.